To an everyday user, typing a web address and pressing enter feels instantaneous. You type a URL and a few milliseconds later, a web page materializes. But what happens beneath that simple interaction is one of the most complex engineering achievements of the modern world. Before a single pixel can be painted, your browser must orchestrate a massive, multi-threaded, cross-continental relay race. It spans OS kernels, distributed global phone books, cryptographic handshakes, and physical hardware routers buried deep underwater. Today, we are peering under the hood to map out every single IPC message, DNS query, TCP packet, and TLS record from the exact microsecond. Hit enter to the arrival of the first byte. The journey begins locally. The network process first intercepting a request checks its ASTS pre-list to ensure the connection enforces HTTPS. Next, it queries its internal memory cache for a valid DNS entry. If it draws a blank, it requests the OS kernel to check the local host file. When local lookups fail, the browser must use the phonebook of the internet, the domain name system. It crafts a UDP packet bound for your ISP's recursive resolver. If the resolver doesn't know the IP, it triggers an iterative recursive search. It asks the root nameserver, which points it to the TLD nameserver for .com, which finally points it to the authoritative nameserver for the domain. The IP address is resolved and returned to the browser, unlocking the destination coordinates. With the target IP address in hand, the browser initiates a layer 4 connection. For standard HTTP.1 or HTTP2, this requires creating a network socket and executing the classic TCP three-way handshake. The browser sends a synchronization flag, or SYN. The server replies with SYN and ASK. Finally, the browser confirms with an ACK. This structural bullet establishes a reliable, ordered stream of communication. However, TCP suffers from a foundational flaw, head-of-line blocking. If a single packet is lost on its journey across the web, the entire stream grinds to a halt while it waits for a retransmission. This is why modern architecture is shifting rapidly toward HTTP3. By abandoning TCP in favor of QIC over UDP, HTTP3 allows independent streams of data to flow concurrently, ensuring a dropped packet on a style sheet won't block your images. An open connection is a vulnerable connection. Before sending raw data, the browser must layer on cryptographic shielding using Transport Layer Security, or TLS. In modern TLS 1.3, this security layer is forged in just a single round trip. The client issues a client hello packaging, its supported encryption algorithms, and a mathematical public key share. The server answers with its own key share, along with its digital certificate. Through Diffie-Hellman key exchange mechanics, both systems calculate an identical cryptographic accession key completely independently. No spy in the middle can deduce it. At the same time, the browser validates the server's certificate against its hard-coded root store of certificate authorities, ensuring that the site you are speaking with is truly who they claim to be. With a secure tunnel open, the browser finally constructs its payload, the HTTP request. Under HTTP, these text headers are compressed using HPACK into binary frames to preserve bandwidth. The request shoots across the web, reaches the server, and triggers backend application logic. The server answers, firing back an HTTP 200 OK response along with the raw payload, bytes of your index HTML file. As those first network chunks stream into the browser's network process, it reads the incoming content type header. The moment it confirms the payload is an HTML document, it flags the browser master process. The browser allocates a fresh, sandboxed isolation chamber, the renderer process. To minimize overhead, a direct data highway is established, streaming raw bytes directly from network socket straight into the renderer process memory space. The raw bytes hit the renderer process, and the final stage begins. The HTML tokenizer treats the document as a live character stream, stepping through state machines to output structural element tokens. But parsing takes time. To keep the engine optimized, a secondary background runs alongside the main parser, the preload scanner. It sweeps ahead through the raw text stream, looking for external resource assets, like CSS sheets, scripts, or web fonts. The moment it detects them, it speculatively dispatches network requests in the background. By the time the main parser finishes building the structural DOM, those asset bytes are already arrived and waiting in memory. This is the complete life cycle of a browser request, a coordinated symphony of protocol systems, operating system kernels, and multi-process sandboxes working in harmony to deliver information across the globe in a fraction of a second. If you want to see exactly how these newly arrived HTML, tokens, and style sheets are transformed into a layout tree and drawn onto your screen, hit subscribe and check out our deep dive guide on the internal Blink rendering pipeline. Drop your questions below, and I'll see you in the next frame.